Imagine holding a small piece of uranium, no larger than a pebble, that holds the energy equivalent of tons of coal. It sounds like science fiction, but it is absolute reality. For decades, nuclear power has quietly supplied electricity to hundreds of millions of people. No sun needed, no wind required. Reactors hum day and night, acting like an unsleeping mechanical heart. Just a single plant can power an entire major city, keeping millions of homes bright all at once. And what surprises many is that nuclear energy produces virtually zero carbon emissions during operation. In a world deeply anxious about climate change, that is not just a minor advantage, it is a massive one. A single kilogram of uranium releases millions of times more energy than the same mass of fossil fuels. That power does not come from burning. It comes from nuclear fission, where atoms split and release hidden strength. It sounds dangerous, but under strict control, that reaction is kept within tightly managed boundaries. The truth is, many nations have relied on nuclear power for half a century, and everyday life goes on entirely normally. If you look strictly at emissions data, nuclear energy is just as clean as wind and solar, often even cleaner. So, a very logical question arises. Why don't we build nuclear power plants everywhere? If it is powerful, clean, and stable, what is holding humanity back? Is it the cost? Is it the risk? Nuclear power is like an extremely sharp blade. Used correctly, it is immensely useful. Used wrongly, the consequences are profound. Or is it the haunting memory of accidents that once stunned the entire world? But before we talk about fear, we need to understand why it was once seen as the ultimate future of energy. There was a time when people believed nuclear energy would provide cheap, limitless power for the entire planet. In some places, that belief still quietly operates behind thick concrete walls. History is not just made of light. It also holds moments that forced the world to completely rethink its path. In this journey, we must confront the deepest fear: how nuclear accidents made the world hesitate for years. When nuclear power goes wrong, the terror doesn't come from raging flames, but from something invisible. Radiation is silent, odorless, and colorless, and the mere thought of it can rob people of sleep for nights on end. Chernobyl in 1986, a failed nighttime test that completely altered the history of the nuclear industry. It wasn't just an explosion. It was an entire region left abandoned, as if time itself had frozen behind concrete walls. Those silent cities became a symbol far more powerful than any scientific report or statistical chart. Then came Fukushima in 2011, when nature challenged designs believed to be fully secure. A massive earthquake, a towering tsunami, and a cascading chain of failures shook public trust. Ever since, phrases like widespread core meltdown have lingered, even if few truly understand the mechanics behind them. The most haunting part isn't the immediate casualty number, but the prolonged uncertainty stretching across years. When a region becomes permanently linked to the word radiation, it carries a fear that transcends national borders. Even when science offers clear explanations, human emotion is simpler. Stay far away from potential danger. After every major disaster, many nations immediately paused projects, shut down reactors, and reviewed their entire energy strategies. Some decided to withdraw from nuclear power completely, despite previously viewing it as an energy pillar. The great paradox here is that statistics show nuclear energy causes far fewer deaths than coal. Yet fear does not follow statistics. It follows collective memory and deeply etched images. And once those memories take root, every proposal to build a new reactor touches a deeply sensitive nerve. Even a tiny risk carries consequences that could span multiple generations. Therefore, the world weighs more than just engineering. It weighs psychology, politics, and social trust. Yet the nuclear industry did not stand still. Modern reactors bear little resemblance to the aging designs of the 1980s. The philosophy of safety evolved. Rather than just fixing errors, engineers design systems where errors are extremely difficult to happen in the first place. One of the greatest shifts is passive safety. If total power is lost, many modern reactors can still cool themselves entirely through natural physical laws. Water circulates via temperature differentials and gravity, eliminating total dependence on electric pumps. This means that even if humans fail to react in time, physics continues to protect the system. After Fukushima, international standards tightened dramatically. Older plants underwent upgrades, while new facilities had to pass extreme worst-case simulations. Furthermore, we now see the rise of smaller units known as small modular reactors, or SMRs. These smaller reactors feature lower output, enhanced control, and mass-producible designs. Some innovative concepts even recycle spent fuel to reduce long-term waste storage pressures. Yet, technology alone does not entirely erase human memory. Often, the hesitation to build new nuclear plants comes down to numbers on a financial spreadsheet. Building a nuclear plant takes not 2 or 3 years, but an entire decade. Unlike wind or solar farms, nuclear projects require complex bureaucratic approvals, geological surveys, and immense safety documentation. With every passing year, budgets swell due to delays or shifting regulatory standards. Investors see massive financial risks because interest accumulates daily before the plant generates a single kilowatt. Some projects experience massive cost overruns, deepening public skepticism. Compounding this is the enduring challenge of nuclear waste. Power is generated for decades, but certain waste products remain radioactive for thousands of years. Society thinks in decades, but nuclear waste requires thinking across epochs. While stored securely in dry casks or deep geological repositories, convincing local communities remains a profound hurdle. Finally, nuclear technology carries an inherent dual-use nature. The physics that generates peaceful electricity is fundamentally linked to defense infrastructure. This dual-use capability requires rigorous international oversight, safeguards, and inspections. In geopolitics, every reactor is not merely an energy asset, but a matter of strategic trust. So, should we build nuclear power plants everywhere? The short answer is, it is not a simple yes or no. Nuclear energy provides massive, stable baseload power that intermittent renewables cannot yet match. It emits nearly zero carbon during operation. It is not a universal solution for every nation, but it demands massive capital, long construction timelines, and complex waste management. The future of global energy transition will not be a single winner, but a balanced mosaic. Nuclear can serve as a stable bedrock for the grid, while wind and solar provide flexible support. Every nation faces unique geographic, economic, and political realities. Nuclear power is neither an angel nor a villain. It is a powerful tool, entirely dependent on how humanity chooses to wield it.